Okay, yaar. So good morning everyone. So so after 1 week again we are continuing the session. So because of some lockdown issues, I was not able to take the class for the last 1 week. Okay, so from today onwards again we are going to continue with this YouTube sessions here, right? Okay. So first of all, let me know whether audio and video everything is clear. So first of all, let me know whether audio and video everything is clear. So if it is not clear, please let me know through chat box here, right? Okay. So if it is not clear, please let me know through chat box, right? So I hope everything is clear here. I hope everything is clear. Okay. So we are dealing with the subject electromagnetics, and in electromagnetics we have started the topic that is transmission lines. Transmission lines, right? Okay. So in transmission lines here, in transmission lines we have studied about transit time effects. In transmission lines we have studied about transit time effects, and then after this we have studied distributive nature along the transmission line. Distributive nature along the transmission line. Okay. So next so after this we have studied we have seen a circuit model, yes or no? Okay. So the equivalent circuit model of transmission line. Okay. So from here we have derived the expressions for what? Expressions for voltages and currents on the transmission line. We have derived the expressions for voltages and currents on the transmission line, and from here we have derived the expressions for voltages and currents, and then after that, so after this we have studied about characteristic impedance here. We have studied about characteristic impedance of the transmission line. Characteristic impedance, which is represented with Z0. Okay. Okay. So before this we have studied one more thing, that is propagation constant, yes or no? So propagation constant, we have studied about propagation constant, that is gamma. Okay. So in general gamma is what? In general gamma is a complex quantity. So gamma is equal to what? Gamma is equal to alpha plus j beta, and the units of gamma is nothing but what? Meter inverse, right? Okay. So these things we have studied. Next we have studied about characteristic impedance, that is Z0, right? Okay. So after characteristic impedance here, so after characteristic impedance we have studied about we have studied the input impedance here. We have seen the expressions for input impedance on the transmission line, right? So next we have studied reflection coefficient on the transmission line, gamma of L. Okay. So these are the topics that we have covered here. These are the topics that we have covered. Okay. So we got the expression for reflection coefficient on the transmission line, and we got the expression for Zin of L, that is input impedance seen on the transmission line, and we got the expression for characteristic impedance on the transmission line, that is Z0, and also we got the expression for a propagation constant, that is gamma. Okay. So we'll just briefly look into these expressions here, what we got, right? So gamma is equal to what? We got gamma is equal to square root of what? Square root of R plus J omega L into what? Into Z plus J omega C. This is the expression we got for gamma, right? So we can write gamma is equal to what? Gamma is generally a complex quantity, so we can write gamma as what? Alpha plus what? Alpha plus j beta, right? Its units are nothing but meter inverse, meter inverse. Next, alpha, for alpha the units are nothing but what? For alpha the units are nothing but Nepper per meter, and for beta the units are nothing but what? For beta the units are nothing but what here? Radian per meter. And also we have seen that 1 Nepper is equal to what? 1 Nepper is equal to 8.68 dB, right? Okay, and what is alpha here? What is the expression for alpha? So I have told one formula here. I have told one formula, that is square root of a plus jb is equivalent to what? Is equivalent to square root of a square plus b square plus a divided by 2 plus what? Plus or minus j into square root of, again square root, a square plus b square minus a divided by 2. So here you are going to get plus sign whenever b is greater than 0, and here you are going to get minus sign whenever b is less than 0. Understood? Okay, so I have told this formula here. So from this formula we have tried to derive the expression for what? Alpha and beta. Yes or no? So what we got here? What we got? So from this expression, by using this formula, we try to get the expressions for alpha and beta. So what are the expressions for alpha and beta we got? Tell me, what are the expressions we got? Alpha and beta. So alpha, we got it as what? Alpha is equal to, we got it as 1 by 2 into square root of r square plus omega square L square, right? Okay, so r square plus omega square L square into what? Into z square plus omega square c square plus rg minus omega square Lc whole to the power of what? Whole to the power of 1 by 2. So this is the expression we got. This is the expression we got. Yes or no? So 1 by 2 into square root of r square plus omega square L square into z square plus omega square c square plus rg minus omega square Lc whole to the power of what? Whole to the power of 1 by 2. So Nepper per meter. So this is the expression we got here for alpha, right? Okay. Okay here. So next for beta, the expression will be what? The expression looks similar, but here in place of plus you are going to get what? You are going to get minus sign. So that is the only difference, right? Okay, so beta equal to, we got 1 by 2 into what? 1 by 2 into, so this is 1 by 2 into here, right? Okay, so 1 by 2 into square root of what? Square root of r square plus omega square L square multiplied by z square plus omega square c square minus of what? Minus of rg minus omega square Lc whole to the power of what? Whole to the power of 1 by 2 radian per meter. Okay, so these are the expressions we got for alpha and beta, right? Okay, see here alpha is not equal to 0 here. Alpha represents what? Attenuation constant. Beta represents what? Phase constant. Here alpha is not equal to 0. Yes or no? So that means we are dealing with what? We are dealing with lossy transmission line. So since alpha is not equal to 0, implies what? Lossy transmission line. So on a lossy transmission line, these are the expressions we got. For gamma we got this expression, and for alpha and beta we got these expressions. Right? Okay. Okay. Yeah. So next after this we have derived the formula for characteristic impedance, that is Z0. So what is Z0 here? Z0 is nothing but what? Z0 is nothing but a forward traveling wave voltage to what? To forward traveling wave current. Yes or no? So if you take the ratio of forward traveling wave voltage to forward traveling wave current, you are going to get what? You are going to get V plus by I plus. Yes or no? So therefore we got V plus by I plus, which is equivalent to Z0. We have derived this formula here. What we got? We got this is equivalent to square root of R plus J omega L divided by what? Divided by Z plus J omega C. Understood? Okay. So characteristic impedance of the transmission line. Characteristic impedance of the transmission line we got by taking the ratio of what? By taking the ratio of forward traveling wave voltage to what? Forward traveling wave current. Understood? And we have seen that this characteristic impedance is depending upon what? Is depending upon the primary constants of the transmission line, or you can say the characteristics of the transmission line. So that is nothing but R, L, G and C. So since it is depending upon the characteristics of the transmission line, we are calling it as what? We are calling it as a characteristic impedance. We are calling it as what here? Characteristic impedance of the transmission line. Right? Okay. So I have told that already for a given transmission line, this characteristic impedance is what? This characteristic impedance is fixed. For a given transmission line, this characteristic impedance is going to be fixed. Yes or no? So it depends upon what? It depends upon how you are designing the transmission line. So once you design the transmission line, this R, L, Z and C values are fixed, and hence this characteristic impedance of the transmission line is also going to be fixed for a given operating frequency. Yes or no? Okay. And also we have seen that this Z0 is independent of what? It is independent of length. It is independent of length of what? Length of transmission line. Length of transmission line. So that means as you move along the transmission line, you are not going to see any changes in the characteristic impedance. Understood? So always remember, the characteristic impedance is what? Is the ratio of what? Traveling wave voltage to traveling wave current. Traveling wave voltage to traveling wave current. Understood? Okay. So you have to keep these points in mind. So traveling wave voltage to traveling wave current, and the value of characteristic impedance will be fixed for a given transmission line. Once you have designed the transmission line, then the characteristic impedance will be fixed for that transmission line for a given operating frequency. And also we have seen that it is independent of what? By seeing this expression, we can say it is independent of what? It is independent of length of transmission line. It is independent of length of transmission line. Okay, so why it is becoming independent of length of transmission line here? Why means here we are taking what? We are taking the traveling wave voltage to what? Traveling wave current. Traveling wave voltage to traveling wave current. Yes or no? So if you consider the forward traveling wave voltage here, forward traveling wave voltage, so that is nothing but what? V plus e power minus gamma x into e power j omega t will represent what? Will represent a forward traveling wave voltage. Forward traveling wave voltage divided by what? Divided by forward traveling wave current. Forward traveling wave current, I can represent it as what? I plus into e power minus gamma x e power j omega t. So this is forward traveling wave current. Understood? So whenever you are taking this ratio, what is happening here? E power j omega t will becoming cancel, and e power minus gamma x will also become what? Cancel. Understood? Okay, so that means it is becoming what? It is becoming independent of what? Independent of x. Understood? Okay, so that means this is the transmission line here. This is the transmission line, right? So this is source and this is load. We have considered from source to load, we have considered it as what? X. So as you move along the transmission line, the characteristic impedance is equivalent to what? It is equivalent to V plus by what? V plus by I plus. So e power minus gamma x will get what? Will get cancelled. That means it is becoming independent of what? It is becoming independent of X. Understood? So it is not going to vary as you move along what? Along the transmission line. Right? Okay. So this is what we have seen here. Right? Okay. Okay. And in general, I have told that this V plus is nothing but what? V plus is nothing but a complex quantity. I plus is also what? I plus is also nothing but complex quantity, and this characteristic impedance is also nothing but what? Is also nothing but a complex quantity. Yes or no? So that's what we got here. Z0 is nothing but what? A complex quantity. Right? Okay. Okay. So I have told that where V plus is equal to what? Where V plus we can represent it as V plus into what? E power j phi, where phi represents what? Well, phi represents initial phase. Where phi represents initial phase of the wave. Okay. I have explained all these things here. In the previous classes itself. Right? So just I am revising, since I have not taken the class for the last 1 week, so that's why I am revising briefly each and everything whatever we have covered in the previous sessions, right? Okay, okay, yeah. So this is all about characteristic impedance of the transmission line, right? So it is for a designed transmission line, this characteristic impedance will be fixed, and it is independent of what? It is independent of length of the transmission line, right? It depends only upon the characteristics of the transmission line, that is R, L, Z and C values. Understood? For a given operating frequency, it depends only upon R, L, Z and C values, which are nothing but the characteristics or primary constants of the transmission line. So and hence Z0 is also called as what? Characteristic impedance of the transmission line. So for a given transmission line, characteristic impedance is fixed and it is not going to depend upon the length of the transmission line, right? Okay, okay. So next we have determined the input impedance on the transmission line. Input impedance on the transmission line. So what is the input impedance of the transmission line here? It is nothing but what? It is nothing but the ratio of what? The ratio of standing wave voltage. Standing wave voltage to what? Standing wave voltage to standing wave current. It is the ratio of standing wave voltage to standing wave current. Yes or no? Okay. So what we got here? Standing wave voltage to standing wave current. So that means if you consider the transmission line here, if you consider the transmission line, okay, so if you consider the transmission line, so from here onwards what we have done here, we have considered the reference as what? Our reference as load. So that means we have considered here L is equal to 0. So we have started moving from where to where? From load to what? From load to source. So from load to source, as you move from load to source, we have considered this as what? We have considered this as L. So from source to load, we have considered this as what? X. So in all our expressions, what we have done here, we have replaced L with what? We have replaced L with minus X. So by that we got the expressions for V of L comma T and I of L comma T. So what are the expressions we got here? That is nothing but V plus into e power gamma L plus V minus into e power minus gamma L multiplied by e power j omega t, and here we got I plus into e power gamma L plus I minus into e power minus gamma L multiplied by what? Multiplied by e power j omega t. And we have replaced this I plus with what? We have replaced this I plus with V plus by Z0 into e power gamma L, and this I minus we have replaced with minus of what? Minus of V minus by Z0 into e power minus gamma L. So plus into minus, here it will become what? Plus into minus will become minus, right? Okay, so here we got minus, right? So this is the expression for I of L comma T we got. Yes or no? Okay, okay, wait. Into what? Into e power j omega t. So these are the expressions for voltages and currents on the transmission line we got. So this is nothing but what? This is nothing but the standing wave voltage on the transmission line, and this is nothing but what? Standing wave current on the transmission line. Okay. Okay, yeah. So why we are seeing the standing wave pattern, all those things I have explained here. So whenever you are having a forward traveling wave whenever you are having a forward traveling wave, so it is going to see what? It is going to see a characteristic impedance of Z0 on the transmission line, and at load, whenever if ZL is not equal to what? Not equal to Z0. So because of this impedance mismatch at the load, what will happen here? A part of the wave will get transmitted to the load, and remaining part of the wave will get what? Will get reflected back. So this is incident wave, and this is nothing but what? This is nothing but reflected wave. So the superposition of this incident wave and reflected wave is going to form what? Is going to form a standing wave pattern. On the transmission line, and hence we are going to see voltages and currents as what? Standing wave patterns on the transmission line. Now if you take the standing wave voltage to standing wave current here, if you take the ratio of standing wave voltage to standing wave current, you are going to get what? You are going to get input impedance seen on the transmission line. So this input impedance seen on the transmission line is very much different from what? From the characteristic impedance of the transmission line. Understood? So characteristic impedance is the impedance that we got by taking the ratio of what? By taking the ratio of forward traveling wave to forward traveling wave voltage to forward traveling wave current. Okay. So whereas this input impedance seen on the transmission line is nothing but what? Is nothing but a ratio of what? Standing wave voltage to standing wave current. That means you are taking the ratio of V of L comma T by what? By I of L comma T. So if you take this ratio, you are getting what? You are getting Zin of L. Right? Okay. Okay. So all these things I have covered here. All these things I have covered already in the previous sessions itself. Right? Okay. Okay. So therefore we got we got Zin of L. We got Zin of L is equal to what? Is equal to we got what here? We got V plus into e power gamma L plus V minus into e power minus gamma L divided by V plus into e power gamma L minus V minus into e power minus gamma L multiplied by what? Multiplied by Z0. Multiplied by Z0. Understood? Okay. So next after this we have started with reflection coefficient. We have started reflection coefficient on the transmission line. So we have represented the reflection coefficient on the transmission line with what? Gamma of L. Gamma of L. Right. Okay. So what do you mean by reflection coefficient on the transmission line here? It is a measure of what? It is a measure of how it is a measure of what? It is a measure of how the reflected wave, how the propagation characteristics of the reflected wave are changing when compared in relatively with respect to what? With respect to the propagation characteristics of the incident wave. Okay. So here what we are doing here? What we are doing? We are comparing the reflected wave characteristics with respect to what? With respect to incident wave characteristics. So characteristics means what here? Characteristics of a wave means what? It is nothing but amplitude and phase. Okay, so here we are measuring how the amplitude and phase of the reflected wave is varying or changing when compared with respect to what? When compared with respect to amplitude and phase of the incident wave. Yes or no? So we have taken the ratio of what? We have taken the ratio here of reflected wave to what? To incident wave. Reflected wave to incident wave. So what we got here? We got here V minus by V plus into what? E power minus 2 gamma L. E power minus 2 gamma L. Right? Okay. Okay. So from here we have derived the expression for reflection coefficient at load. So at load what will happen here? At load means what? L is equal to 0. So at load the reflection coefficient gamma L is equal to what? Is equal to V minus by what? V minus by V plus. V minus by V plus. So this is what we got. So since this V minus is a complex quantity and this V plus is also what? This V plus is also complex quantity. This gamma L is also nothing but what? This gamma L is in general is nothing but what? Is nothing but a complex quantity. Is also nothing but a complex quantity. Right? Okay. Thank you, Vikas. Thank you. Okay. So at load L is equal to 0. So here the reflection coefficient is nothing but what? V minus by V plus. So generally this gamma L is nothing but a complex quantity. So complex quantity means I can represent it as what? I can represent a complex quantity in polar form. How I can represent here? It is going to have what? Both magnitude as well as what? As well as phase shift. Okay, so a complex quantity I can represent in terms of polar form in this manner. So it is going to have magnitude as well as what? As well as phase shift. So this represents the magnitude of the reflection coefficient at load, and this represents the phase shift of the reflection coefficient at load. At load. Okay. So this is what we have derived here. This is what we have derived, right? So next, by substituting this expression here, what we are going to get here? You are going to get the reflection coefficient on the transmission line, gamma of L, is equal to what? This V minus by V plus. V minus by V plus is nothing but gamma L, where gamma L is nothing but magnitude of gamma L into e power j phi L. So I can represent this one. I can represent this one in this manner. That is magnitude of gamma L into e power j phi L. Now here e power minus 2 gamma L. So here this gamma represents what? This gamma represents a propagation constant. Yes or no? This gamma represents propagation constant. constant, that is gamma is nothing but what? Alpha plus j beta. Gamma is nothing but alpha plus j beta. So if you substitute alpha plus j beta here, what you are going to get here? You are going to get e power minus 2 alpha L into e power minus j 2 beta L. So from here we got the expression for reflection coefficient on the transmission line as gamma of L is equal to what? Magnitude of gamma L into e power minus 2 alpha L into what? E power j of phi L minus 2 beta L. Phi L minus 2 beta L. Okay. Okay. So Veera Vikas, try to share the session to your friends, to your friends here. Try to share the session to your friends. Okay. So that most of the students will get benefited, right? Okay. So share this session and like this session to as many students as possible here, right? Akash Mishra, please speak in Hindi. See, in this is a GATE Academy global channel here. This is not a main channel. So this is a GATE Academy global channel. So here in a global channel, the lecture series will be in English only. Okay. So the way of communication will be in English only, right? So if you want in Hindi, so then you can attend Sonal Sir's lectures here. So it is going on in GATE Academy 2.0 channel, right? Okay. So there Sonal Sir is taking the lectures in Hindi, in EMT, okay, for EMT, right? Okay. So here the purpose of this channel is the main mode of communication will be in English only. The teaching will be in English only, right? Okay. So anyway, for this EMT subject, we are providing the lectures both in English as well as in what? As well as in Hindi. So in English, I am providing the lectures, and in Hindi language, Sonal Sir is providing the lectures in GATE Academy 2.0 channel, right? Okay. So you can go through those lectures here. It depends on your comfort here, right? Okay. Whichever language that you are comfortable, you can go through that. Okay. Okay, so the reflection coefficient on the transmission line is equal to what? Magnitude of gamma L into e power minus 2 alpha L into e power j of phi L minus 2 beta L. Okay, so this is the expression we got here. This is the expression we got for the reflection coefficient on the transmission line. Reflection coefficient on the transmission line. Which transmission line here? We are dealing now with what? We are dealing with lossy transmission line. We are dealing with lossy transmission line. Okay, so on a lossy transmission line, this is the expression for reflection coefficient we got. Understood? So now if you observe, this represents what here? This represents the amplitude. This represents the amplitude of the reflection coefficient. Amplitude of the reflection coefficient. And this represents what? This represents a phase of what? Phase of reflection coefficient. Phase of reflection coefficient. Right? Okay. Akash Mishra, do you complete waveguide? So right now I cannot guarantee anything here. So right now I am teaching transmission lines. Okay, so once it is completed, then later I will plan here. Later I will plan for further topics of the EMT also, right? Okay, so anyway I will try to cover most of the topics here, right? Okay, so as of now I am dealing with transmission lines. We will continue with the transmission lines. So once we have completed this transmission lines topic, then I will plan for other topics also, right? Okay. So here this represents amplitude of the transmission line, amplitude of the reflection coefficient, and this represents phase of the reflection coefficient. So what we can observe here is the reflection coefficient on the transmission line is a function of what? Is a function of length. It is a function of length, right? Okay. So as you move on the transmission line from where to where here? From load to source. See, L represents what? L represents the movement from where to where? From load to source. Yes or no? So we have considered our reference. Now we have considered our reference as what here? We have considered our reference as load. Now we are moving from load to what? From load to source. So as you move from load to source here, the amplitude of the reflection coefficient, is decaying exponentially. Yes or no? Okay, on a lossy transmission line, as you move from load to source, the amplitude of the reflection coefficient is decaying exponentially, and phase of the reflection coefficient. What is happening to the phase of the reflection coefficient here? See here, phi L is nothing but the phase of the reflection coefficient at what? At load. Okay, so now at load L is equal to 0, phi L represents the reflection coefficient at load. Now as you move from load to source, this L value is going to increase. So as this L value increases, this 2 beta L value is also going to increase. So that, and you are subtracting this 2 beta L value from phi L. So that means what happens to the overall phase shift here? You are subtracting 2 beta L from phi L. Yes or no? So that means the total phase shift will become what? It is going to decrease. Yes or no? So as L value increases, that means as you move from load to source, this L value increases. As L value increases, this 2 beta L is going to increase, and you are subtracting this 2 beta L from phi L, and hence the overall phase shift is going to decrease as you move from where to where? From load to source. Right? Okay. So these are the things we have concluded here. Right? So here I have told that on a lossy transmission line, the amplitude of reflection coefficient, decays exponentially, as you move from load to what? As you move from load to source. Right? Okay. And what happens to the phase here? And phase of reflection coefficient decreases. Yes or no? Phase of reflection coefficient decreases. This is the phase. Yes or no? Phase of the reflection coefficient decreases as you move from where to where? As you move from source to what? As you move from load to source. Right? So these are the conclusions we have drawn here. Right? Okay. So from these expressions, we have got the expression for reflection coefficient gamma L. I am not deriving again here. We got the expression for reflection coefficient in terms of what? In terms of ZL and Z0. Yes or no? So what you are going to get here? Gamma L, we got ZL minus what? ZL minus Z0 divided by what? Divided by ZL plus Z0. So this is the expression we got for the reflection coefficient. Right? Okay. And this is the reflection coefficient at what? At load here. At load. This is the reflection coefficient at load. Right? So this ZL in general a complex quantity, and Z0 is also in general a complex quantity, and hence gamma L is also nothing but what? In general it is a complex quantity. So this is the reflection coefficient at load. Okay, expression. This is the expression we got for the reflection coefficient at load. Right? Okay. So next we got the expression for Zin of L. We have derived the expression for Zin of L. So what is the expression for Zin of L here? We got Zin of L is equal to what? Is equal to Z0 into 1 plus gamma of L divided by what? 1 minus gamma of L. So this is the expression we got for Zin of L. Okay, so this is the relation here. This is the relation between what? This is the relation between the input impedance seen on the transmission line and the reflection coefficient. This is the reflection coefficient on the transmission line. This is the reflection coefficient at any point on the transmission line. Understood? So this is the reflection coefficient exactly at what? Exactly at load. Understood? Okay. So this is the relation here. This is the relation we got between what? Between the input impedance seen on the transmission line and reflection coefficient on the transmission line. Right? Okay. Okay. So next. Okay. So next we got Zin of L. Zin of L is equal to what? We have seen one more expression, that is Zin of L is equal to, I have derived this one here, Z0 into what? Z0 into ZL plus ZL plus Z0 into tan H gamma L divided by what? Divided by Z0 plus ZL into tan H gamma L. Okay, so these are the expressions we have derived here. These are the expressions we have derived for the input impedance seen on the transmission line. Right? Okay. Okay. So these are the things that we have derived from the previous session, in the previous sessions, right? Okay. Okay, so all these topics we have covered, and also I have explained how to determine the angle here, how to determine the angle. So if it is real part and imaginary part, this is imaginary part. If the complex number lies in first quadrant, how to determine the angle. If the complex quantity lies in second quadrant, how to determine the angle. If it lies in third quadrant, or if it lies in fourth quadrant, how to determine the angle. Yes or no? Okay, so I have told in terms of what? In terms of general argument, and also I have told in terms of principal argument. Okay, so in general argument, the range of phi, the range of angle we will consider as what? We will consider from 0 to what? From 0 to 2 pi. Understood? Whereas in case of principal argument, there we will consider the angle as what? The angle varying from where to where? Minus pi to what? Minus pi to plus pi. So here we will consider both negative angles as well as what? Positive angles, and here we will consider only what? Positive angles. So this we call as general argument, and this we call it as a principal argument. So here we will get the angles in terms of negative angles as well as what? Positive angles, but here the angles must be what? The angles must be positive. Understood? Okay, so I have explained all these things here. I have explained all these things in the previous lectures itself. Okay. Okay. So these are the things that we have covered. These are the things that we have covered, right? Okay. Okay. So now in this session, we try to solve some problems. We try to solve some problems based on this, right? Okay. 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 So this is the question here. This is the problem. Okay. So see here, what is the question they are asking here is a voltage wave at 1 gigahertz traveling on a transmission line. A voltage wave of 1 gigahertz is traveling on a transmission line in positive x direction. In positive x direction is given by what? Is given by V of x comma t. V of x comma t is equivalent to what? Is equivalent to V plus into e power minus alpha x into what? Cos of omega t minus beta x plus phi. Understood? Okay, so this is how they have given what? They have given the voltage that is traveling on what? The voltage wave that is traveling on the transmission line. So this represents what? V plus into e power minus alpha x represents what? Represents the amplitude of what? Amplitude of the wave, and this represents what? This represents the phase of what? Phase of wave. Understood? Okay. Okay. Yeah. Okay. So this is the voltage wave they have given on the transmission line. So then they have given the primary constants. The primary constants of the line are R is equal to what? R is equal to 0.5 ohm per meter, L is equal to 0.2 microhenry per meter, Z equal to what? Z equal to 0.1 mho per meter, and C equal to 100 picofarad per meter. The wave has a 30 degrees phase. The wave has what here? 30 degrees phase at t equal to 0 and x equal to 0. The wave has 30 degrees phase at t equal to 0 and x equal to 0. Find instantaneous voltage and peak voltage at x equal to 1 meter and t equal to what? And t equal to 100 nanoseconds. Understood? So this is the question they have given here. So what they have given here? So this is the transmission line. Let us say this is the transmission line and this is source, right? And here this is nothing but what? This is nothing but load. This is nothing but load, right? Okay, so from source to load we will consider as what? We will consider it as x, right? Okay. Okay. Yeah. So this is source and load. So along this direction we will consider it as what? We will consider it as x, that is from source to load, right? Okay. Okay. So they have given the voltage wave. They have given a voltage wave traveling on a transmission line in positive x direction, in positive x direction. That means they have given what? They have given a forward traveling wave. They have given a forward traveling wave on the transmission line. Yes or no? See, in generally what we got here, forward traveling wave, how we have represented? V plus into what? V plus into e power minus gamma x into what? Into e power j omega t. Yes or no? So this represents the forward traveling wave. Right. So this I can represent it as what? If I take the real part of this one here, if I take the real part of this one, then what I'm or I can represent in this manner. Okay. If I take the real part of this one, how I can represent here? So real part of this V plus into what? Into e power minus gamma x, that is e power minus alpha x into e power minus j beta x into e power j omega t. So real part of V plus into what? Into e power minus alpha x into e power j of omega t minus what? Omega t minus beta x. Yes or no? So now this V plus I have told that V plus represents what? V plus represents a complex quantity. So in general we will represent V plus as what here? V plus into what? Into e power j phi, where this phi represents what? Phi represents the initial phase. Right. Okay. So initial phase of the wave. Now if I consider this real part of magnitude of V plus into e power j phi, you can represent in this manner. Okay. So magnitude of V plus into e power j phi, here e power minus alpha x multiplied by what? E power j of omega t minus beta x. E power j of omega t minus beta x multiplied by e power j phi, I can write it as what? E power j of omega t minus beta x plus what? Plus phi. Understood? So multiplied by what? Multiplied by here e power minus alpha x. Now if I take the real part of this one, what you are going to get? You are going to get V plus into e power minus alpha x into what? Cos of omega t minus beta x plus phi. Understood? So that means the forward traveling wave here, the forward traveling wave you can represent in terms of what? In terms of real time also. Yes or no? Okay. Here we have represented the wave in terms of what? In complex manner. We can represent the same thing in terms of what? In terms of real time solution in this manner. Right. Okay. So this is the expression they have given here. So you have to understand that this represents what? This represents the amplitude of what? Amplitude of the forward traveling wave, and this represents what? This represents the phase of the wave, and you have to keep in mind that this phi represents what? This phi represents the initial phase here. Phi represents what? Initial phase. So what do you mean by initial phase here? It is the value of phi at which t equal to 0 and x equal to 0. Whenever t equal to 0, x equal to 0, if the wave is having some phase shift, that phase shift is called as what? Initial phase of the wave. Right? Okay. Okay. So I have already explained here what do you mean by this initial phase shift and all those things. Right? Okay. So this is the waveform they have given here. This is the waveform they have given. So you have to understand that this is the wave and this is the amplitude of the wave, and this is the phase of the wave. So they have given the wave that is propagating in positive x direction, which is having some initial phase shift phi. Okay. So here the initial phase shift phi they have given as what? This initial phase shift phi they have given as 30 degrees. They have given as 30 degrees. Understood? Okay. 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 And here in this problem they have given R value, L value, Z value and C value. That means they have given primary constants of the transmission line, and now they are asking find the instantaneous voltage and also peak voltage at x equal to 1 meter and t equal to what? And t equal to 100 nanoseconds. So at this instant of time and at this location you have to determine what? You have to determine the instantaneous voltage, and also you have to determine what? Peak voltage of the wave. Understood? Okay. Okay. Now see here. So in order to determine that, what is needed here? What is needed? See here. So they have given that V of x comma t is equal to what? Is equal to V plus into e power minus alpha x into cos of omega t minus beta x plus what? Plus phi. So this is the expression they have given for voltage. Understood? So they are asking to determine, at x equal to 1 meter, and at t equal to what? At t equal to 100 nanosecond, they are asking what is the instantaneous voltage? Understood? And also they are asking what is the peak value of the voltage? At x equal to what? At x equal to 1 meter and at t equal to 100 nanoseconds. Okay, so they are asking the instantaneous voltage. This is instantaneous, and this is nothing but what? Peak voltage. Okay, so these two you have to determine, right? So in order to determine these things here, first of all you have to determine what? You have to determine this voltage, yes or no? You have to determine this V of x comma t. Understood? See, in V of x comma t, what we know here? They have given the frequency. As what? Frequency, I think they have given 1 gigahertz, right? Frequency is 1 gigahertz, right? Okay. So they have given the frequency as what? 1 gigahertz. So that means we know omega value. Understood? Okay, and we know this phi here. Phi they have given as what? Phi is nothing but initial phase. So phi they have given as 30 degrees. So we know this phi also, right? Okay, so and they are asking at x equal to 1 meter. That means we know this x value also. At x equal to 1 meter they are asking, and at instant t equal to what? 100 nanoseconds. So at t equal to 100 nanoseconds. Right. So we know omega value, we know t value, we know x value, we know phi value. Understood? So here also we know x value at x equal to what? 1 meter. So what are the unknowns here? So we don't know this magnitude of V plus. Right. Next, what we don't know here? We don't know this alpha value. We don't know this V plus value, and we don't know this beta value. Understood? So in order to get this instantaneous voltages and peak voltages, what you have to determine? You have to determine this magnitude of V plus, and you have to determine this alpha value, and you have to determine beta value. Okay, so if you want to determine alpha value and beta value, which means what? You have to determine what? You have to determine propagation constant gamma. So gamma is equal to what? Gamma is equal to alpha plus j beta. Understood? Okay, so you have to determine alpha value as well as what? As well as beta value. Next, you have to determine magnitude of V plus, and also you have to determine magnitude of what? Magnitude of V plus. Right? Okay. So now here they have given one more clue here. That is okay. So in the problem you have to add one more thing here. I think I have missed that one. Okay, so just add one more thing. So write down this one. When x equal to 0 and t equal to 0. When x equal to 0, t equal to 0. When x equal to 0, t equal to 0, or you can consider simply, you can write in this manner. Okay. So in the problem given or consider, you can write consider. Okay. So consider V of 0 comma 0. V of 0 comma 0 is equivalent to V of 0 comma 0 is equivalent to 8.66 volts. Okay, so consider V of 0 comma 0 is equivalent to what? Is equivalent to 8.66 volts. Okay. So in the problem, just add this one here. So you have to include this one here. In the problem itself, you have to include this one. So that is, consider V of 0 comma 0 is equal to what? Is equal to 8.66 volts. So that means at x equal to 0 and t equal to 0, they have given the instantaneous voltage as what? 8.66 volts. Understood? Okay. So I have missed this data here. Just include this one, right? Okay. So this is the problem here. This is the problem. Okay, up to here, this is the problem. Okay, so they have given V of 0 comma 0, V of 0 comma 0. They have given V of 0 comma 0 is equal to what? Is equal to 8.66 volts, 8.66 volts, right? So this is also given in data itself, given in data, right? Okay, okay. So now see here. Now, what is V of 0 comma 0 here? If you put V of 0 comma 0, okay, if you put V of 0 comma 0, what you are going to get? Put x equal to 0 and t equal to 0. What you are going to get? Here put x equal to 0, here put t equal to 0, here x equal to 0. What you are going to get? Magnitude of V plus into e power minus 0, that is 1. Cos of what? Cos of omega t will become 0 minus beta x will also become what? 0. What is remaining? Cos phi. Understood? Okay. So at V of 0 comma 0 here, at V of 0 comma 0, okay. So therefore V of 0 comma 0, so therefore V of 0 comma 0 is equivalent to what? Is equivalent to magnitude of V plus e power minus alpha x will become what? Will become 1. Why? Means x equal to what? 0. Next, what is left out here? Cos of what? Cos of omega t. Omega t will also become 0 because t equal to 0. Minus beta x, x equal to 0. So beta x will also become 0. So what is left out? Cos of what? Cos of phi. So phi is nothing but what? Phi is nothing but 30 degrees. Phi they have given as 30 degrees. This is the value of phi. Understood? Okay. So at x equal to 0 and t equal to 0 and t equal to 0, so they have given this voltage here. They have given this voltage value as what? As 8.66 volts. 8.66 volts. Okay. So this is equivalent to what? This is equivalent to magnitude of V plus into cos 30. What is cos 30 here? Cos 30 is nothing but what? Is nothing but root 3 by what? Root 3 by 2. Right? Okay. So therefore magnitude of V plus is equal to what? Is equal to 2 into 8.66 divided by what? Divided by root 3. So if you do this, what you are going to get? So 2 into 8.66 divided by what? Divided by root 3. So you will get 9.9997. So that means I can take it as what? Approximately 10 volts. I can consider it as approximately 10 volts. Okay. So magnitude of V plus, we got it as what here? Magnitude of V plus, we got it as 10 volts. 10 volts. Right? Okay. So what are the things that we have to determine? We have to determine V plus and we have to determine alpha value and beta value. So here we have determined V plus value. Right? Okay. So we got V plus value. We got V plus value. So V plus, magnitude of V plus, we got it as what? 10 volts. 10 volts. Right? Okay. Okay. Here. Next, you have to determine alpha and beta. So how to determine alpha and beta here? So how we can determine alpha and beta? So here they have given what? They have given R, L, Z and C values. They have given R, L, Z and C values. Right? Okay. Here they have given R, L, Z, C and also they have given the frequency. Okay. So from this we have to determine what? From this you have to determine alpha value and beta value. Yes or no? So how we can determine here? How we can determine? See here. So R is equal to 0.5 ohms, L is equal to 0.2, Z is 0.1, C is 100. Okay. Okay. So I am writing the data here. I am writing the data. Okay. So R is equal to 0.5 ohm per meter, L is equal to 0.2, 0.2 micro Henry per meter, Z equal to 0.1 mho per meter, C equal to what? C equal to 100 picofarad per meter. So I hope the data is correct here. I have written, I think so, 0.5, 0.2, 0.1, 100, right? Okay. So anyway, once we will check here. So 0.5, 0.2, 0.5, 0.2, 0.1, 100. Okay, perfectly correct. And frequency is what? Frequency is 1 gigahertz. Frequency is 1 gigahertz. This implies omega is equal to what? 2 pi into 10 to the power of 9 radian per what? Radian per second. Okay. Okay. Yeah. So see here. Here this is nothing but what? This is nothing but lossy transmission line. Yes or no? Lossy transmission line. Okay. So for a lossy transmission line, what is alpha here? What is alpha? We have derived these expressions here. Yes or no? Okay. So alpha is equal to what? See, I have revised everything. Here I have given the expression for alpha and all those things. Yes or no? Okay. See, this is the expression for alpha. This is the expression for alpha, and this is the expression for what? This is the expression for beta. Understood? Okay. So you can directly use these expressions and determine what? Determine alpha and beta. See, if you observe these two expressions here, see, both are looking what? Both are looking similar. The only difference is here you are having plus sign and here you are having minus sign. That is the only difference here. That is the only difference. So whenever you are determining these things, what you will do is first determine this term, that is r square plus omega square L square term. Next determine z square plus omega square c square term. Next determine this term. So calculate all the three terms here. Just substitute all these three terms. You are going to get what? Alpha value. And if you substitute all the three terms and if you put here minus, then you are going to get beta value. Understood? Okay. So this is one way here. This is one way. Sir, we don't want to remember all the formulas and all those things. If you don't want to remember all those formulas, then you can do directly. That is, we know that gamma is equal to what? Gamma is equal to square root of what? Square root of r plus j omega L into what? Into z plus j omega c. So you have to substitute r value, omega value, L value, here z value, here omega value, here c value. Then you have to simplify. Okay, so it will become somewhat complicated here. It will become somewhat complicated. Okay, so if you want, you can convert this rectangular form. If you want, you can convert this rectangular form. Just I am explaining here what are the procedures that you can follow. Okay, so based upon your comfort, you can follow anything, right? Okay, so what you can do here is you can convert this into polar form. You can convert this into polar form. Okay, so if you convert this into polar form, you are going to get what? You are going to get, let us say you are getting some magnitude. Let us say you are getting some magnitude. Okay, so I am representing this. Okay, so that I am saying, okay, so you are going to get some magnitude. So that magnitude I am representing with R1. Let us say that magnitude you are getting magnitude of R1. Okay, next. What is the phase shift here? Phase shift, let us say e power j phi 1. You are getting e power j phi 1. So in this manner you can convert. You can convert this rectangular form into what? Polar form in this manner. Next, for this one, you can determine what? You can determine its magnitude. Let us say its magnitude is magnitude of R2, and here the phase shift is, let us say, e power j phi 2. Understood? So now what you can do here? What you can do? So square root of magnitude of R1 into what? Magnitude of R2 into what? Into e power j phi 1 plus what? E power j phi 1 plus phi 2. So this is what you are going to get. Okay, so here R1 is equal to what here? Magnitude of R1 is equal to square root of what? Square root of R square plus omega L whole square. Next, magnitude of R2 is nothing but what? Square root of z square plus omega c square. Right. Next, phi 1 is nothing but what? Phi 1 is nothing but tan inverse of what? Tan inverse of omega L divided by R. And phi 2 is nothing but what? Phi 2 is nothing but tan inverse of what? Tan inverse of omega c by z. Understood? So you can calculate all these things and you can substitute here and you can determine what? Gamma value. Understood? Okay, so what you are going to get finally? You are going to get square root of magnitude of R1 into what? Magnitude of R2. So if you take the phase shift outside the root, then you can write it as what? E power j of phi 1 plus phi 2 divided by what? Divided by 2. Okay, so if you take the phase out of the root, then you have to divide with what? You have to divide with 2. Okay, so I hope you know all these things here, right? Okay, okay. So this is how you can calculate. This is one method. This is one method. Right? Okay. Okay. So or otherwise you can directly apply what? You can directly apply the formula. Yes or no? So what is that one here? We know alpha. We have already derived here. We have already derived the expressions for alpha and beta. So alpha is equal to what? What we got? 1 by 2 into r square plus omega square L square multiplied by what? Multiplied by z square plus omega square c square plus what? Plus Rz minus omega square Lc, right? Okay, so this is under root, so whole to the power of what? Whole to the power of 1 by 2. So this is the expression we got for alpha. Yes or no? So by substituting in this, we can get what? You can determine alpha value. You can determine alpha value. Yes or no here? Okay, okay. So here you have to determine this term, you have to determine this term, and you have to determine this term, and you have to determine this term. So if you calculate all these three terms, then just by substituting these three terms, you are going to get what? You are going to get alpha value. Understood? So similarly you can determine beta value also by putting minus sign here, right? Okay. So if I try to determine r square plus omega square L square, r square plus omega square L square is equal to what? R value is how much here? R value is, I think, 0.2 whole square, 0.2 whole square. I will do the analysis approximately here, approximate calculations I will do. Okay. Okay. So omega square is nothing but what? 2 pi f. 2 pi f means what here? So omega square L square means I can write omega L whole square. Yes or no? So what is omega L? 2 pi f. 2 pi f means 2 pi into 10 power 9 into L value. L value is how much here? They have given 0.2 microhenry. Yes or no? 0.2 microhenry. So that is 0.2 into 10 to the power of minus 6. So this is omega L. So omega L whole square. Understood? So this is equivalent to what you are going to get. Here you will get 0.04. Yes or no? Plus here you are going to get 4 pi square into 0.04. Okay, 0.04 into what? Into 10 to the power of, so here 10 power 9, here 10 power 9, and here 10 power minus 6. What you are going to get? 9 minus 6, that is 3. You are going to get 10 power 3. Yes or no? So 10 power 3 whole square, that is 10 power 6. So this is what you are going to get here. Now here if you put pi square is approximately 10. Understood? Okay. So you are going to get here 40. This one will be 40. Okay. Okay, so 40 into 0.04 here, 40 into 0.04. How much you are going to get here? 40 into 0.04. So you are going to get 16, right? Okay, so you will get 1.6 here. You will get 1.6. So here you are going to get 1.6 right now. Yes, 1.6 into 10 power 6. Here you are getting 0.04. Understood? So you can neglect this 0.04 when compared to this value. Yes or no? 1.6 into 10 to the power of 6 is very large value. This is very large value when compared to what? 0.04. Understood? So you can neglect this one. So this term is equivalent to what? This value is approximately equivalent to what? 1.6 into 10 to the power of 6. 10 to the power of 6. Understood? Okay. Now similarly you can determine z square plus omega square c square. Z square plus omega square c square. So this is the value of r square plus omega square L square. Right? Okay. Okay. So this is the value of r square plus omega square L square. So next you have to determine what? You have to determine z square plus what? Plus omega square c square. So which is equivalent to what here? Z value is how much? Z value is how much? 0.1. Yes or no? Z is 0.1. So 0.1 whole square plus omega. Omega is 2 pi into f, that is 10 power 9. C is 100 picofarad. 100 picofarad, that is 100 into 10 to the power of minus 12. So whole square. So this is omega c whole square here. Whole square. Understood? Okay. Okay. So now if you observe here, here 10 power 9, 10 power minus 12. So you are going to get 10 power minus 3. So this 100 I can write it as what? 10 square. Okay. So 10 square into 10 power minus 3, you are going to get what? 10 power minus 1. Right. Okay. So you are going to get here, you are going to get 2 pi into 10 power minus 1 whole square. So that is 4 pi square. 4 pi square into what? Into 10 power minus 2. Into 10 power minus 2. That's what you are going to get here. So 0.1 whole square is also nothing but what? 0.1 whole square. You can write it as what? 10 power minus 2. Right. So this implies 4 pi square. I can pi square value approximately you can take it as 10. So 4 into 10 will be 40. Right. Okay. So 40 plus 1, that is 41. So you will get 41 into 10 power minus 2. Right. Okay. So this is approximate value here, approximately. Why means I have taken pi square as 10, approximately I have taken 10. So I am getting 41 into 10 power minus 2. So this is nothing but what? This is nothing but 0.41. This is nothing but 0.41. So therefore z square plus omega square c square is approximately equal to what? Is approximately equal to 0.41. 0.41. So this is the value we got here. This is the value we got. Right. Okay. Okay. So next, what is the other term you have to determine here? Other term is nothing but what? Rg minus omega square Lc. Rg minus omega square Lc. Okay. So next term is Rg minus omega square Lc. So once you determine these two terms here, okay, once you determine these three terms, then you can determine alpha value as well as beta value. Right. Okay. So next is Rg minus what? Minus omega square Lc. So this value you have to determine. Okay. So this is equivalent to R value is how much here? R value is what is R value here? I forgot. R value is 0.2, right? Correct, no? R value is 0.2. My God. R value is how much here? 0.5, na? L value 0.2, Z value 0.1. So remaining all values are correct. R value I have taken wrongly. Okay, no problem here. Here no problem. Because anyway, if you put 0.5 also here, okay, if you put 0.5 here, you are going to get what? You are going to get you will get 0.25. You will get here 0.25. Okay, so still you can neglect here. Still you can neglect this 0.25. You will get here 0.25 here. Okay, so still you can neglect this 0.25. Okay, still you can neglect 0.25, so you can write approximately 1.6 into 10 power 6. Okay, so the calculation will not be affected here for this value, right? Okay, so you will get the same value. So Z we have taken correctly, omega C everything we have taken correctly, so no problem. So next here Rg minus omega square Lc. So R is how much here? R is 0.5. R is 0.5. Z is 0.1. Z is 0.1 minus omega is 2 pi 10 power 9 square. Yes or no? Whole square. L into C. L value is how much? L value is 0.2 microhenry. 0.2 microhenry. C value is 100 picofarad. 100 into 10 power minus 12. Right? Okay? Okay. So if you do this here, if you do this, what you are going to get here 10 power 9. So here you are going to get 4 pi square, 4 pi square into 10 power 18. So here 10 power 18 and here 10 power minus 18 will get what? Will get cancelled. So 4 pi square I can write it as what? Approximately 40. Approximately 40. So 40 into 0.2 into 100. 40 into 0.2 into 100. Okay. So what you are going to get here? 40 into 0.2 is nothing but what? Is nothing but 8. Yes or no? 8 into 100. 8 into 100. So approximately this value will be 800 here. Approximately you will get this value will be 800. Okay. So here, correct now? Okay. Right. So this value will be 0.05. 0.05. So 0.05 minus 100, you can write approximately what? You can write approximately minus 800. Yes or no? Okay. So 0.05 minus 800. So this value is very large when compared to this one. So you can write approximately minus 800. So this is nothing but what? Rg minus omega square Lc value. Okay. So we have determined all the three terms here. We have determined all the three terms. So just substitute all these things here. Just substitute all these things. So alpha is equal to what? Alpha is equal to 1 by 2 into what? 1 by 2 into square root of r square plus omega square L square, that is 1.6 into 10 power 6 multiplied by what? Multiplied by z square plus omega square c square, that is 0.41. Okay. So 1.6 into 0.41 into 10 power 6. So 0.41 into 1.6. So you will get 1.6 into 0.41 into 10 power 6 under root, right? Plus of Rg minus omega square Lc. So this value we got it as minus 800. So this value is minus 800. Okay. So whole to the power of what? Whole to the power of 1 by 2. Whole to the power of 1 by 2. Okay. So what is this value here? What is this value? So 1.6 into 0.41 into 10 power 6 square root of answer. Okay. So you will get a whole to the power of what? Whole to the power of 1 by 2. Okay. So you will get this value here. You will get this value. This value is approximately 810. You got this value as approximately equal to 810 here, right? Okay. Okay. So therefore alpha is equal to what? Alpha is equal to 1 by 2 into 810 minus 800, that is 10, right? So whole to the power of 1 by 2. So 2 ones, 2 5s. So what you are going to get? Square root of 5. So what is square root of 5 here? What is square root of 5? So square root of 5 is 2.23. So you will get 2.23 Nepper per meter. 2.23 Nepper per meter. Okay. Okay. Yeah. So why I am going through this calculation means here it is just simply multiplication here. Just you have to multiply these two and you have to subtract. There is no need to deal with complex numbers and all. Okay. You can directly calculate alpha value and beta value with these things. Right. Okay. So there is no need to find magnitude and then phase and all those things. If you go through the previous procedure, that whatever I have told, this procedure. So here you have to deal with a complex quantities, yes or no? So here you have to determine the magnitude and then phase shift and all these things. Okay, so instead of doing this one, I have followed this one because we have already derived these expressions. So once if you solve 1 or 2 problems here, if you solve 2 to 3 problems, okay, so based on these expressions, then it is not that much tough to remember this formula. Understood? Okay, okay. So this is 1 by 2, here you have to put bracket. Okay, okay, so this is alpha value, right? So what we got here? We got 1 by 2 into 10, that is square root of 5, that is 2.23 Nepper per meter. Now what is beta value here? What is beta value? See, there is no need to calculate again beta value. So what we can do here? So what is the only one thing? Here in place of plus, what you have to put? You have to put minus. Then you are going to get what? You are going to get beta value. Understood? What is the only difference here? The alpha expression and beta expression both looks similar, but here in place of plus you have to put minus for beta value. Yes or no? Okay, so just put here minus sign here. What you are going to get? So beta is equal to 1 by 2 into, so this value is 810. So in place of plus put here minus. So minus of what? Minus of 800. Okay. So whole to the power of what? Whole to the power of 1 by 2. Right? There is no need to determine again. Right? Okay. Just put here minus sign. So that is the advantage here. Okay. So this is equivalent to 1 by 2 into 810 plus 800 here. 810 plus 800. So you will get 1610 whole to the power of what? 1 by 2. So what is this value here? Divided by 2 square root of 1. So you will get a 28.37 radian per meter. So this is the approximate value of beta. Yes or no? Okay. So therefore we got alpha value as well as what? Beta value. So alpha is equal to 2.23 Nepper per meter. And beta is equal to what? Beta is equal to 28.37 radian per meter. Okay, so these are the values we got for alpha and beta. Right? Okay, so we have determined alpha value as well as what? Beta value, and we got V plus. Yes or no? Magnitude of V plus. What we got here? We got 10 volts. Yes or no? Magnitude of V plus is equal to what? Is equal to 10 volts. Okay, so these are the 3 parameters that we have to determine. Yes or no? In order to determine the instantaneous voltage. And peak voltage. So these are the things you have to determine. So we have determined all these 3 parameters. Yes or no? Now we know they have given that V of x comma t is equal to what? Is equal to magnitude of V plus into e power minus alpha x into cos of omega t minus beta x plus what? Plus 5. Now we know all the values here. This magnitude is nothing but what? 10, and this alpha is nothing but 2.23. Right? Okay. Next, this omega is nothing but 2 pi into what? 2 pi into 10 power 9, and this beta is nothing but what? 28.37 radian per meter, and this phi is nothing but what? Remember, beta you are representing in terms of what? Radian per what? Radian per meter, and here phi they have given us what? 30 degrees. See here 28.37 radian per meter. The units of x is nothing but what? The units of x is nothing but meters. So here meters will get cancelled. So that means this term you are calculating in terms of radians. This term finally you are going to get in terms of radians. And here phi, if you put directly 30 degrees, then you are going to get wrong answer. Yes or no? See, this is you are taking in degrees, and this you are taking in radians. You should not add radians to what? Radians to degrees directly. You have to convert what? You have to convert either radians to degrees or degrees to radians. So this is the mistake generally the students will do. Understood? What they will do here is just they will substitute beta value and x value, and the result of beta x you are going to get in terms of radians, and they will add this to what? To directly to 30 degrees, which is what? Which is wrong. Okay, so you have to convert both this beta x and phi both into what? Both into radians or both into degrees. Then only you can perform addition or subtraction. Yes or no? Okay. Okay, here. So that means here I can write this 30 degrees as what here? I can write this 30 degrees as pi by 6 radians. I can write this as pi by 6 radians. Understood? Okay, or you can convert, you have to convert this 28.37 radians, you can convert into what? Into degrees. You have to convert either this into degrees or this one into radians. Okay, okay, so any of this you have to follow. Right, so here omega you are representing, omega is nothing but what? Radian per second. Its units are nothing but radian per second. Here it is seconds. So here also you are getting in terms of what? Finally you are getting in terms of radians. So beta x also you are getting in terms of radians. So convert this into what? Convert this into radians. So everything must be in what? Must be in the same units. So whenever you are calculating the phase, so this is the mistake generally the students will do. They don't convert the radians into degrees or degrees into radians. They will just substitute the values whatever they have given. Understood? Okay, so don't do that mistake here. Whenever you are calculating the phase, so convert each and every term into same units. Okay, so here I have converted each and everything into what? Into radians, each and everything in terms of radians. Understood? So 30 degrees you can write it as what? Pi by 6. Right? Okay, so now they are asking the instantaneous voltage here. They are asking the instantaneous voltage at what? At x equal to 1 meter and t is equal to what? At t is equal to 100 nanoseconds. So at this instant they are asking what? They are asking the instantaneous voltage. Okay, so at this instant what is the voltage you are going to get? So that is V of 1 comma what? That is V of x is equal to 1 comma t is equal to what? T is equal to 100 nanoseconds. That means 100 into 10 to the power of minus 9 seconds. So at x equal to 1 meter. So at this instant they are asking what? Instantaneous voltage. So just substitute in place of x, substitute 1 meter, and in place of t substitute 100 nanoseconds. Understood? So what you are going to get here? So here you will get 10 into what? e power minus alpha x. Alpha is nothing but what? Alpha is nothing but 2.23. X is nothing but what? X is nothing but 1. Okay, so multiplied by cos of what? Cos of omega value is 2 pi into 10 to the power of 9 into what? T. T is 100 into 10 power minus 9. 100 into 10 power minus 9. Minus what? Minus beta x. So beta value is 28.37 into x. X value is what? 1. So x value is 1. Right? Okay. So x value is 1 plus phi. Phi is nothing but what? 30 degrees, that is pi by 6. Okay. So if you calculate this value, you are going to get what? You are going to get instantaneous value of voltage at x equal to 1 meter and t equal to 100 nanoseconds. Okay, so now for this function, what is the peak value? This is nothing but what? This is nothing but peak value. So at this instant they are asking peak value. That means they are asking this value. That's it. Understood? Okay. Okay. Yeah. So peak value of v of x equal to what? X equal to 1 meter comma t equal to 100 nanoseconds. 100 nanoseconds is equivalent to what? Is equivalent to 10 into what? 10 into e power minus 2.23. E power minus 2.23 into 1. That means 2.23. Okay, 2.23 volts. So this is the peak value. This is the peak value of the voltage at this instant. Understood? Okay. So determine this here. Determine this, what you are going to get. So I think you can do this one here. I think you can do this one. Okay. Now it becomes very simple. Right. So e power minus 2.23. So we got here 1.23 1.075 1.075 into cos of, here 10 power minus 9, here 10 power 9 will get cancelled, right? Okay. Okay, so if you do this one here, this value what we got here, what you got, calculate that one. Okay, so 2 so convert, first of all, everything we have converted into radians here, right? Okay, so calculate this cos of in terms of what, in terms of radians. So 2 pi into 100 minus 28.37 plus so what you got here, calculate this value, calculate this value here, calculate this value. So this multiplied by this one, this multiplied by this one, you are going to get what, you are going to get, this is the instantaneous voltage here, this multiplied by this value. So calculate this value here, right? Okay, so peak value is nothing but this one, so that is nothing but 1.075, right? So what is this value here, we got 2 pi 200 minus 28.37 plus 800 by 6. So I think I am getting minus 0.9098 here. Okay, so you can check this one here, you can check this one, what you are getting, right? So 1.075 into what, into minus 0.9098 into 1.075. So this is equivalent to what, this multiplied by this, you are going to get minus 0.978. So this is the instantaneous value of the voltage. This is the instantaneous value of the voltage at x equal to 1 and t equal to 100 nanoseconds. So if you want only peak value, so the peak value is nothing but what? The peak value is nothing but the coefficient of what? The coefficient of this cos function. This is the peak amplitude. Yes or no? This is the peak amplitude of this function. Okay, so the peak amplitude of the wave is nothing but what? 10 into e power minus 2.23, that is 1 point plus 1.075. Okay. 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 So I think we have done the calculations correctly. I hope so. Okay. So you can check this once here. You can check this one, and if there are any calculation mistakes, let me know here. Let me know if there are any calculation mistakes. Right. Okay. Okay. So I hope everything is correct. I hope everything is correct. Right. So just here, just we are practicing how to apply these formulas to the problems and how to solve the problems. Understood? So just for practice I have taken this question. Okay. Okay. So once you have to get familiar, how to deal with these complex quantities and how to deal with this formulas and all the, how to apply these formulas and all these things. Okay. So that's why I have taken this problem. Okay, so I hope it is crystal clear here. I hope this problem is crystal clear, right? Okay, so with this here, I am winding up the session for today. So tomorrow exactly at 10 a.m. here. Tomorrow exactly at 10 a.m. we are going to start the session, right? Okay, so every day in our Gate Academy Global channel, EMT lecture series will be conducted every day at 10 a.m. Understood? Okay. Okay. So and the mode of language will be in English here. Mode of teaching will be in English, right? Okay. So every day at 10 a.m. in our Gate Academy Global channel, this EMT lectures will continue. So tomorrow also exactly at 10 a.m. we are going to start the session. Okay. So until then, take care. Bye bye.